Hello again everybody! In today's video, we're gonna go from this, to that, and finally to this. Let's get started. Let's say we have a mass on a spring and we want to find out what is the mass's position at some time t, after we pull the spring and let it vibrate back and forth. Well, we need some calculus to answer this question. We can just start off by writing one of the equations of motion, which is just simply the net forces is equal to ma. We know at least one of the net forces, that's going to be negative kx is equal to ma. That's just the restorative spring force with the constant k and then the change in position x. Now you clicked on this video because we want to talk about damping forces, so let's also say that this spring is being slowed down by some retarding force minus some constant L times the velocity of the spring. And of course L depends on what is slowing it down. It might be the friction of the air, it might be, let's say it's dipped in water or maple syrup, whatever it's slowing it down. L is just a constant, and the velocity is there to signify that it is being slowed down while it is in motion. So let me just rewrite this in differential form by writing out the definition of the acceleration as d squared x divided by dt squared, and the velocity as dx dt. And we will suddenly have a second order linear ordinary differential equation. Allow me to just rewrite everything that we've written so far by dividing the mass on both sides, and then moving all of this stuff over to the right hand side so that we have an equation that equals 0. Now here's where we get into a little bit of hocus pocus with some math magic. Since we're going to do this with standard notation, we're going to start off by saying that capital letter D is going to be equal to d over dt, the derivative. Then we're going to say that 2b is equal to L over m. Then we're going to say that omega squared is equal to k over m. Let's just plug in everything that we've written out so far. Alrighty, now one final step that we need to do is to divide out all of these x's and just get rid of it. Well, we've ended up in this situation where this kind of looks like something that we could use the quadratic formula with. Instead of x equals negative b plus or minus the square root, etc., etc., we're going to say that d is equal to negative 2b plus or minus the square root of 4b squared minus 4 omega squared, all divided by 2. And the entire reason why we put 2b in the first place is so that we could just simplify this into negative b plus or minus the square root of b squared minus omega squared. Now because we have a plus or minus sign on the square root, this is going to give us two solutions. We're going to say that the first solution with d is going to equal negative b plus the square root, and then we are going to say that the second solution is negative b minus the square root. Now I could go down a rabbit hole of math, but it's pretty much unnecessary at this point just to figure out what is damped motion and what are its applications. So if you do not know how to get the results, you just need to simply trust the math and focus on how to apply the answers we are about to write down. Our first type of damped motion is going to be called overdamped motion, and this only happens if b squared is greater than omega squared. And the solution looks something like this. The position as a function of time is equal to some constant a times an exponential minus d1t. d1 is just the stuff that we solved earlier with the square root, plus another constant b, e negative d2 times t. Okay, so we have some constants that make this solution still incomplete. In order to solve for these constants, we need to use some sort of initial condition, boundary constraints, or just see what happens when we test our problem at the limits, like something such as t equals infinity. If we were to do that for this problem, we know that our spring is going to be returning to x equals 0 at the very end once t equals infinity, and even once we plug in infinities over here, and then 0 over here, we're just going to get that a equals b. Okay, now instead of two unknown constants, we have one unknown constant. Well, how do we figure that out? Well, let's just test it out at the initial position. Plug in t equals 0, and you should know the initial position at least. And then a is just equal to x initially, whatever that position is. I mean, these are just examples. Of course, every problem is unique, and you should adapt to them accordingly. Now, when we graph out overdamped motion, this is going to have something that looks like this. If we just graph this with a position versus time graph, we're going to get something that looks like this. A very slow decay, eventually reaching its equilibrium at x equals 0. Our second type of damped motion is going to be called critically damped motion, and this only happens if b is equal to w. Well, this is going to have an equation of x as a function of time is equal to, in parentheses, a plus b, these are constants, times the time, in parentheses again, e to the negative bt. And once we graph this on an x versus time graph again, this time we're just going to get a straight sudden drop off, and it reaches x equals 0 at rest much more faster than overdamped motion. Most likely it's not even going to oscillate a single time. Our final type of damped motion is going to be underdamped motion, and this only happens if omega squared is greater than b squared. And this is going to have a solution of x as a function of time, e to the negative bt, in large brackets, some constant a times sine lambda t, we'll talk about that in a little bit, plus another constant b cosine lambda t. And in this case, we're saying that lambda is equal to the square root of omega squared minus b squared. Again, if you don't know where these solutions come from, you don't have to worry, you don't have to stress about it too much. You just need to know how to apply these problems. And this is going to have a solution that looks something like this. It will oscillate, however, with every oscillation, it comes closer and closer and closer to 0. Now, mathematically speaking, it's always going to hover around 0 without actually reaching 0. But we live in the physical world, and we can say that it's pretty damn near close to 0. I hope this video helped you guys out, and good luck out there.